So, are you ready to go to work?
Yep. Great.
So,
So thanks for
the
having
next
me.
speaker is Yin Choi Cheng from CUNY Graduate Center, who talks about order type of shifts of morphic words. Please.
Yep. So thanks for having me. The topic of my talk is order type of shifts of morphic words. This is a topic given by my advisor, Professor Kevin O'Brien. So this technically falls under the category of combinatorics on words, but some of the examples that I will be giving today have some kind of number theoretic flavor. So hopefully the audience will enjoy. So let's describe the problem that we want to consider. Given a morphic word W, with starting letter A0 followed by A1, A2 over a linearly ordered finite set, we consider it set of shifts, Wi, where W sub I is the ith shift of W. Essentially, we are removing the first I letters from W, that's the ith shift of W. We want to order these shifts lexicographically, and we want to know the order type of this set of shifts. In short, we have a bunch of stuff, we want to order them, and we want to see how they look like. Is the ordering the same as natural numbers or integers or rational numbers or others? But first, let's define some of the relevant terms that we've seen here. In this talk, we're going to consider right infinite words over a finite alphabet, which is denoted by sigma sub m. This is the set of integers from 0 to m-1, where m is greater than or equals to 2. We let sigma sub m star be the set of all finite words over sigma m. We define a morphism on sigma m to be a map from sigma m star to sigma m star, such that phi of u v equals to phi of u phi of v. The operation between is concatenation. We can extend this definition to infinite words. For example, I can apply a morphism phi to a right infinite word W. And we do so by applying phi to each of its letters. And next, we have a special type of morphism. Let n be greater than or equals to 2. We define an n-uniform morphism phi on sigma m to be a morphism, such that the length of phi of alpha is n for all letters alpha in sigma sub m. And now for a morphism phi is prolongable at alpha if phi of alpha is equals to alpha u, where u is some non-empty word. If phi is prolongable at alpha and w is an infinite word over sigma sub m, such that w is equals to phi omega of alpha, meaning it is the limiting word obtained by applying phi repeatedly on alpha and its subsequent images. Then we say that w is the fixed point of phi starting with alpha. So how do we get this expression over here? Well, we first apply phi to alpha, and we have alpha u. Then we apply phi to alpha u. Alpha gives alpha u, u gives phi of u, and we continue this process over and over again. And with that, note that if we apply phi to any shift of w, the image is also a shift of w. And now w is said to be purely morphic if it is a fixed point of some morphism. And w is n-uniform morphic if it is a fixed point of some n-uniform morphism. And w is morphic if it is a purely morphic word under some coding sigma, going from sigma m to sigma m prime. And here are some examples. First one, to a Morse word with prefix 01101001. This is the two uniform morphic word generated by the morphism mu on sigma 2 defined by mu of 0 equals to 0, 1, and mu of 1 equals to 1, 0. The Fibonacci word with prefix 0, 1, 0, 0, 1, 0, 1, 0 is the purely morphic word generated by the morphism phi, once again, over sigma 2 defined by phi of 0 equals to 0, 1, phi of 1 equals to 0. And note that any purely morphic word and uniform morphic word is also considered as a morphic word if we pick the identity coding. Now, for the sake of giving an example of a morphic word, we can also view the two-most word as the image of the word W, which is generated by the uniform morphism phi on sigma 3 defined by phi of 0 equals to 0, 1, phi of 1 equals to 1, 0, phi of 2 equals to 2, 0, under some coding from sigma 3 to sigma 2 by defined by sending 0 and 2 to 0 and 1 to 1. And next, here are some of the common order types that will be relevant in this talk. The first one, we consider the set of non-negative integers. We have a clear minimum element, and each element has an immediate successor. The order type of this set is omega. And let's consider the reverse. The order type of the set of non-positive integers is omega star. Given a linearly ordered finite set S of n elements, its order type is n. And if S is instead infinite and dense in the sense that pick any two elements in S, I can always find some element that is right between them. Then it has the same order type as Q, the set of rationals intersecting one of the four intervals from 0 to 1. We can also mix and match these order types. So consider the set of all non-negative integers, and suppose that all non-negative even numbers are smaller than all positive odd numbers, and we keep the order among numbers with the same parity. So what does this ordering look like? We start with the even numbers. We have 0 being the smallest number, followed by 2, and by 4, and 6, and so on. And since all positive odd numbers are larger than all even numbers, 1 is larger than 0, 2, yada, 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 which is followed by 3, then by 5, and so on. Each of these groups, let's start with the group of even numbers. It has order type omega. The group of odd numbers also have order type omega. So together, the set has order type omega plus omega, or omega times 2. And now, once again, we consider a set of non-negative integers, and suppose that 0 is the largest. And prime powers p to the n with positive exponents are larger than other positive numbers, and we keep the order among these positive numbers. So the smallest number would be 1, followed by 6, followed by 10, and so on. And among prime powers p to the n, p1 to the n1 is less than p2 to the n2 if the base p1 is less than p2, or they have the same base but exponent, n1 is less than n2. So after the first group of numbers, which has order type omega, it's followed by 2, 4, 8, and so on, which also has order type omega, followed by powers of 3, and so on. And since there are infinitely many primes, we know that there are infinitely many of these groups. And if we consider these groups as elements, the order type of these groups is also omega. And so the order type of this set becomes omega times omega plus 1, since we have a clear maximum element, or omega squared plus 1. So now we have defined all the relevant terms. We can look at some examples. Let's start with the 2m squared. So previously I've mentioned that it is the fixed point of the 2 uniform morphism mu, defined by mu of 0 equals to 0, 1, of 1 equals to 1, 0, starting with 0. Alternatively, we can directly define the letters inside the 2m squared. We let W of bracket square bracket K denote the kth letter in W, with K being greater than or equals to 0. Then the kth letter of the 2m squared is equals to 1 if the binary expansion of K has an odd number of 1s. And the kth letter is 0 if the binary expansion of K has an even number of 1s. So now, what does the order of its shift look like? Well, since the 2m squared is closely related to the binary expansion, we want to check the first 2 to the n shifts of the 2m squared for the first field n and observe the pattern. So let's start with n equals to 1. We take a look at the 2m squared and its first shift. The first shift starts with a 1, 2m squared starts with a 0, so obviously t is less than the first shift. N equals to 2, we include the second shift and the third shift, and we have the following order. Next, n equals to 3, we include 4 more shifts. So what do we notice here? So observation number 1, we notice that the new shifts in each case interleaves with the old ones in the previous case. So n equals to 1, that's the starting case. N equals to 2, the new shifts are second shift and the third shift. N equals to 3, the new shifts are the fourth shift up to the seventh shift. And we see that they are stuck right between some of the old shifts from the previous cases. And observation number 2, we notice that on the right-hand side, the first shift remains as the lexicographically greatest element on each stage. And that is true in general. We can show that the first shift is the lexicographically greatest shift of the 2m squared using the following facts. Choi, in his 1912 paper, proved that the 2m squared is overlap free, meaning it does not contain any string of the form CX, where C and X are finite strings and X can be empty. Burstow in 1994 proved that the lexicographically greatest infinite overlap free word over sigma 2 starting with 0 is precisely the 2m squared, which also implies that its shift are all overlap free. With that, we can show that the first shift is the greatest shift of the 2m squared by a simple contradiction argument. Suppose not, then we will be able to construct a proper shift of the 2m squared starting with 0 that is somehow greater than the 2m squared itself. Now I want to prove the claim that the new shifts interleaves with the old shifts at each stage. And we do that by proving the following 5 inequalities. And I will skip the proof, it's kind of messy. Now we notice that with the exception of the second inequality, each of these new shifts are sandwiched between two old shifts, and we can check that the upper bounds are all unique and the lower bounds are also all unique. So for the second inequality, it doesn't have a lower bound because this new shift becomes the new smallest element on that stage. So with that, this implies that the order type of shifts of the 2S word, or OT of T, is the same as the order type of the rationals intersecting the half open interval 0, 1, including 1 excluding 0. So we have one example done. What about other morphic words? We first get the easy cases out of the way. Suppose that W is ultimately periodic, not necessarily morphic. Then the set of its shift must be finite. Why is that? Let's take a look at a simple example. Let's suppose that this is a word over sigma 3, and it's obvious that it's ultimately periodic after the pre-period. So the number of distinct shifts here would be 5 plus 2 of them. The 5th shift is equals to 7th shift, equals to 9th shift, and so on. 6th shift is equals to the 8th shift, equals to 10th shift, and so on. So the set of shifts of this particular word is simply 7. Therefore, we only consider cases when W is aperiodic, meaning not ultimately periodic. For example, what is the order type of shifts of the Fibonacci word, which we have previously defined? Let's look at something a little bit more random. What about this word W prime, which is generated by the morphism defined below? It's over sigma 5. And what about this morphic word obtained by applying some coding on W prime? Well, the answer to that is the shifts are all dense. Now, how can we tell that? We're going to give a sufficient condition which shows that an aperiodic morphic word W over sigma M has order type being dense, the order type of its set of shifts. In particular, suppose that W is morphic and aperiodic, and it is the image of a purely morphic word W prime over sigma sub M prime under some coding sigma. And more importantly, suppose that the starting letter of W prime occurs at least twice in W prime. Then we can conclude that the order type of shifts of W must be dense. Now, previously, we have mentioned that if the order type of some set is dense, then it could be one of the 4 order types. But in this case, when we're dealing with morphic words, it could only be one of the 3. Specifically, it cannot have a lexicographically least element and a lexicographically greatest element at the same time. And we can also read from the morphism that generates the word W prime to determine if the starting letter occurs twice in W prime. In particular, let that starting letter be alpha. It occurs twice, at least twice in W prime, if and only if it occurs in the image of phi of beta for some beta in sigma M prime, other than being the starting digit or starting letter of phi of alpha. So now let's move on to the outline of the proof. The strategy is we want to pick 2 distinct shifts I shift and J shift of W, and I want to find another shift that's right between them. So pick these two arbitrary shifts of W. They must be the same because W is aperiodic. And let D be the smallest integer such that the deflector of the I shift is different from the deflector of the J shift. This corresponds to the top left picture of the 4 pictures below. Next, we look at the pre-image. Since W is aperiodic, W prime must also be aperiodic. We let a starting letter be alpha, then W prime equals to phi omega of alpha for some morphism phi prolongable on alpha. Now we want to pick Q large enough such that the length of phi Q of alpha is greater than the maximum of I and J plus D. And since alpha occurs at least twice in W prime, we can pick some K greater than or equals to 1 such that the K letter of W prime is equals to alpha. And we let L be the integer such that the L shift of W prime is equals to phi Q of the K shift of W prime. So this corresponds to the pictures on the right-hand side in red. We started with W prime and the K shift of W prime. They both have the same starting letter alpha. Then we apply phi to the Q to both of these words. Now W prime being a fixed point of phi remains the same after phi to the Q is applied to it. Whereas phi to the Q of the K shift of W prime is some L shift of W prime. And they have at least a common prefix of length L. And now when we go back to the image W, there are 2 cases to consider. The first case, if W is less than the L shift of W. In this case, the difference first occurred outside of the first L letters. And now we shift both of these words by I. The first word becomes the I shift of W. The second word becomes the L plus I shift of W. Since the first difference remains in both words, we know that the L plus I shift is still greater than the I shift of W. Now, how do we justify that the J shift is greater than the L plus I shift? Well, notice that since L is greater than the maximum of I and J plus D, I plus D remains in the originally first L letters. In the J shift, we know that its deflector is greater than the deflector of the I shift, which means that it's greater than the deflector of the L plus I shift. So we have the desired order. Now we have a corollary regarding binary purely morphic words. For any aperiodic binary purely morphic words W, the order type of the set of shifts of W must be dense. And we can show that by showing that the starting letter of W must occur twice in W. So I know that I'm running out of time. So here's a quick comment about the Fibonacci word. So we know that the order type of shifts of the Fibonacci word must be dense. because of the theorem. But which order type does it have out of the three? We can show that the order type of the Fibonacci word is the set of rational numbers intersecting the open interval 0, 1, meaning it doesn't have a least or the greatest element. And we can show that by using the second order expression. Given any shift of the Fibonacci word, we can find a shift whose index in the second order expansion is of the form 10 to the n, and that would be smaller than the given shift as long as n is large enough. And to find something that's larger than it, we look for a shift whose index in the second order representation is of the form 10 to the n, followed by a 1. As long as n is large enough, the corresponding shift must be greater than the given shift. And that's the end of my talk.
Well, thank you very much. Are there any quick questions before we move on?
I have a quick question. I think it's slide 4 or 5. The Fibonacci representation relates to a binary representation of a Fibonacci number.
Mhm.
And the other one would be on the complexity of we build the algorithm straight as it's shown compared to the insertion sort, assuming that we know the patterns, or we can match the patterns to a database. So the first question is on the slide 4 or 5 concerning the Fibonacci binary sequence that you represent. If you are talking about matching a Fibonacci number in a decimal representation, I mean.
Can you move it to slide 4 or 5 so we can see which?
Yeah, which slide are you referring to?
Any of the Fibonacci examples, the binary sequence, is that the binary representation for a decimal, a Fibonacci number in decimal? Okay. Like 1, 2, 3, 5, etc., and so on. In other words, if it is a Fibonacci, this number in binary, if I translate it to a decimal notation, will it match a decimal Fibonacci number, or a Fibonacci word is just another term?
Oh,
that's all.
I see. So if we start with 0 and we apply v to it,
Right.
it gives us 0, 1. The length
Right.
is 2. And of course, when we start with 0, the length is 1.
Right. Okay.
And now
so,
when we apply it, apply
Okay,
v
all right.
twice to 0.
All right. So the pattern is what is matching a Fibonacci number. Okay.
Exactly.
I mean the length of the pattern. Okay. And the second question is, I think if an algorithm describing what you just said is implemented, if you're familiar with insertion sort, what kind of comparison we could, complexity wise, we could argument between the two. That's basically what it is. Because the kind of shift that you represent are very likely to be compared to an insertion sort in some aspect.
I haven't thought about that at all. Yeah.
Maybe you can continue in a breakout room because it's time to move on to the next talk.
All right.
Okay, thank you so much. Thank you. Thank you very much.